It is my pleasure to introduce our last speaker for this afternoon session, Karin Reinhold Larsson. The title of her talk is Endpoint Bounds for Variational and Jump Inequalities for Convolution and Read Operators.
Thank you, Rinal, for inviting me to be a speaker in this session. I think it's a wonderful endeavor that you're doing, and that allow us an extra way of communicating our work. So the story starts with square functions that, as many of you know, they had been central in Martingale's theory, and from Martingale's theory, then it percolated to harmonic analysis and ergodic theory and operator theory, right? So the results for the martingales is that if you have a martingale and you look at the differences and you construct the sum of the square of the difference and with the square root, that's the standard square function. And Bull-Hurdle proved that the square function is equivalent to the maximal function, right? So f star is the supremum of the fn's. And later, Berger-Davis extended it to the case p equal 1. So we have also looked at square functions in ergodic theory, but where ANs are the regular ergodic averages, and you do the similar procedure. As far as I know, I don't think we have proven an equivalence, so that's something I need to write down. But there are bounds for the square functions in L2, and there is a weak 1-1 result in L1. So this was a result in 95 by Jones, Ostrowski, and Rosenblatt. So they also later in 88, they look at not only the square function, but the variational sum that is, oh, well, it's kind of hard to write. Let me see if I can use a pen. I'm not sure. Okay. So this is the variational norm. It's not exactly a norm, it's a semi-norm. But anyway, we look at any sequence nk, and then you look at the difference of two consecutive terms in that sequence, and do the similar square function. But we will see that there are results for the variational norm when S is larger than 2, because actually this comes from martingales as well. For these variational norms, the case S equal to fails, and there are examples that do that. So if you want to handle the case that S equals 2, you instead look at these oscillation norms where you had to fix the sequence in advance and then look at terms that are bounded within that sequence. And that that is bounded in LP for P between 1 and infinity, and both of these norms are bounded that is, they're weak 1-1 operators, right? Now, the other thing is that at the L infinity side, because you're taking these differences and you're taking as an infinite sum, it's more difficult to expect that you have an L infinity bound. But what you can actually prove is that there is a mean bounded oscillation result. So these operators then will take a function in L infinity and produce a function that is of bounded mean oscillation. So there's another set of averages that arise from convolutions with a measure. So we'll define it by this equation. So you take a probability measure on the integers, and you have a measure preserving transformation tau on a probability space, and you construct this operator. So this operator is a contraction because mu is a probability. And then the natural question is what happens with when you iterate this operator. So iterating this operator ends up being the operator that results by doing the nth times convolution of the measure. So Bellow, Jones, and Rosenblatt in 1994 showed that if the measure satisfies this bounded angular ratio condition, then the maximal function for these operators is a bounded operator in LP. And in the way of proving the boundedness of this maximal function, they ended up having to bound this square function. Right? So what they actually prove is that this square function is bounded in L2, and from L2 they did an interpolation kind of argument to go from the interval from 1 to infinity, but excluding the endpoints, right? Now, what this bounded angular ratio means is that if you look at the Fourier coefficients of your measure, of your probability measure, then it has this approach. So if this circle is the unit circle, right, that's 1, you are approaching 1 in a non-tangential way. So you have so that's what, this means that the spectrum of the measure will live in a region of this form. Now, Roger Jones and myself also looked at the variation and inequality corresponding to these convolution operators. At that time, we only did it in L2, but now there are updated results. So the two endpoints that I want to talk about are what happens in L1 and what happens in L infinity. So a little bit of history about this operators is that if your probability measure has this property, which basically would be like the variance. So it has bounded variance or bounded second moment, and is centered. So it's the variance because the expected value is 0. Then this maximal function is a bounded operator in L1. And however, this method requires you to take derivatives of the Fourier transform of the measure, and it does not extend to higher dimensions. So part of my thesis was to look at this maximal function and see what can be done in higher dimensions, and I was able to bound it. I mean, show that it's weak 1, but it require, instead of a second moment, it require a second plus something, right? And there was a bound on what that epsilon is. And so far as I know, nothing else has been done for C to the D in general, because I mean, we are constricted by the techniques. Now, I didn't put it here, but there are examples of where the conversions fails. So the supremum. Well, when you have the maximal function bounded, you can prove conversions of the convolution averages. But there are examples of measures which, of course, do not satisfy the bounded angular ratio for which the convolutions fail to converge. And that is a work of Lossert. So by looking at Lossert and what and see what else could be done in between, I had a student, my student Chris Wendrichovich, constructed it showed that it is possible to get measures that are not centered, which do not have the second moment, and yet have the maximal function bounded. Have a weak 1 result. So at that time, I mean, the proof was quite complicated, but later on, I saw these 2 results, one by Dangi and one by Cooney, that explain the situation a little bit better. So essentially, Dangi showed that if 1 minus the Fourier transform of your measure in absolute value is approximately similar, it has to be similar to a power of t, then you have a result. In fact, he also proved, I'm going to talk about Reed operators in a minute. He proved that under that condition, the convolution operator is a Reed operator in L1. And Cooney in 2016 showed that, well, actually you can do something, you can extend it to cases where the Fourier transform, the Fourier transform is dominated by a function. Basically, you still want to, so this difference over here, a 1 minus mu hat, what Cooney did is making this less than some rate function. So if you didn't want just t to the alpha, then you can extend it to other kind of rate functions which have certain properties. So you need to control the first derivative and you need to control the second derivative in a particular way. All right. So perhaps this makes it very close to Dange's condition, but there are extra functions that you can do this way. So Reed operators satisfy these conditions. So, well, they need to be power bounded, but in whatever space you are working, they need to have this condition. They need to satisfy this condition. Okay. So the question is, well, if you can prove that it's Reed in L2, would it be Reed in every LP? And so I saw this paper by Kelly, which actually was really beautiful. Not Kelly, sorry, Blunke, by Blunke, that used a Cayley transformation to actually show that if you have a power-bounded operator that is Reed in one LP and is bounded in another, is power-bounded on any other, in some other LQ, then you can interpolate in between. So that would be, it would be Reed strictly between P and Q. So that means that if you have, so if our operators are Reed in all two, and they are bounded in all LP, like the convolution operators are, then they are Reed in all the LP except at the endpoints, right? So we cannot decide that on the endpoints. So I don't know if it is possible to construct an operator that is Reed in all the LPs except L1, right? But at least we have an answer for, let's see, I want to go back to that. Wait. Okay. At least we have an answer for these convolution operators. So because again, Cooney in the same paper showed that the measure that has all those required conditions is weak L1, is weak L1 Reed. But if we add another extra condition that the function itself is less or equal, essentially less or equal than t times its derivative, then it's actually Reed in L1. So at least now we know what Reed in at least that the convolution operators are also Reed in L1. Now, why do we look at Reed operators? Well, they're very interesting. And they have, what happens with them is that there is a lot more tools to work with them, right? There is a functional calculus. So, and that was the work of Lemerdi. So Lemerdi based his work on this work for sectorial operators. So if you saw the picture for the bounded and angular condition. So if you do 1 minus the operator, you have the cone going the other way. So you will get the 0, 0, and then you have a sector going that way. So this is about the spectrum of operator being in a certain sector. So there's a lot of research doing on sectorial operators, and in particular, there is an H infinity calculus for them. I will mention what that is in a minute. What Lemerdi did is realize that when you have a RIT operator, then you can translate sectorial operators into, I mean, you can translate the RIT into sectorial anyway. The thing is that he was able to show that you also have a functional calculus for RIT operators, okay? And when you have this this functional calculus, you can also do this representation. You can do the Cauchy integral representation when you have RIT operators, and that is really powerful. Again, remember that we are dealing with a bounded angular condition, so you approach one in a sector like that, right? So the spectrum of your operator it has a particular way that approaches one, and because of that, you can do the Cauchy integral, and then you will have something that is properly bounded. So these regions are called Stolz conditions, the Stolz regions. So the thing is, when the spectrum is in a region like that, then you have a resolvent condition. So the resolvent is bounded, and this is a proper representation. So when you have that, then, it's like, if, I'm not saying it, I didn't say that, well, if you have functions that are holomorphic, right? So if you have functions that are holomorphic, I can do this, I can apply the function to operator and represent it over a stall condition, a Stolz region, sorry. So when we're using that so the definition of functional calculus is that if you apply a holomorphic function to your operator, then it's bounded by a uniform constant and the supremum of that function on the region where you're doing the representation. So armed with that, Lemerdi then look at the case of the square function when p equals 2. So if we put p equals 2 and you raise it to the power 2, then you have the finite, the partial sums of this square function becomes a holomorphic function. Okay, and then you can do the representation, and then you can have a result in L2. Then what was interesting also about this work is that to extend it to LP, he used the Kinchin inequality and translated the LP results, the LP sums into sums with Rademacher functions. By representing with sums of a Rademacher function, then you can use equivalence of the LP norms with the L2 norms. But you're always having the problem that that's good as long as P is between 1 and infinity, and you cannot handle with that the P equal 1 and the P equal infinity. So I'm putting here is similar, where it actually should be having less or equal. And there is a constant, and the constants depend on the P, the parameter P. And of course, they blow up at P equals 1. But anyway, so not only Lemerdi was able to prove a square function, so he teamed up with Zhu, and they have a couple of papers where they also tackle extended square functions and variation and oscillation norms. So for all of them, using similar techniques, you have results in LP for any P strictly between 1 and infinity. So you already talked about this slide. So with a student, we looked similar to what Lemerdi was doing. We look at the generalized square function, and we were able to show, so there is an interplay between this parameter and this parameter. So if the condition is that, well, there's also the parameter by which you use the variational norm, I mean the sum. So if you have a strict inequality, then these operators are bounded in L1, actually bounded in L1. And the variational norm for that operator is also bounded in L1 for any S larger than 1. Now, the interesting cases are when you have equality in there. Okay, so for that, we couldn't use just general techniques that apply to any read operator. We have to drop down to the convolution operators. So for the convolution operators, then now notice that there is an equality here. So these theorems are interesting in the equal case. So if you have your square function bounded in L2, then it is also weak 1, 1. Okay, so in particular, the case that Lemerdi was looking at, Lemerdi and company, is this type of a square function. So we can show that that one is also weak 1, 1. And we also look at the variational inequalities. Of course, we did it in general, but again, so if we can show that it is bounded in L2, then it's weak 1, 1. But Lemerdi had only looked at the same case where the beta is 2m minus, well, if this is 2r. So if we put 2r minus 1 over there, then we have, because if we put 2r minus 1, this is bounded in L2. And then and in that case, we have a weak 1, 1 result for the variation and inequalities and for any s larger than 2. And when you want to look at the s equal 2 case, then you have to drop down to the oscillation, for which we also have a result. So I didn't put a sketch of the proof. Oh, I'm running out of time. Whoops. So anyway, on the other side of the situation, we look at what happens in L infinity, and we run into some problem there. Just as a reminder, if you have, well, it doesn't have to be L infinity, but what is in here is a mean oscillation. So you look at, this is the average of your function on an interval, and then you look at the averages of the differences in that interval. So BMO means that this quantity, the mean oscillation is bounded. But it turns out that sometimes it's not bounded by a universal constant, and instead it depends on a function. So it depends on a function that depends on the interval. Okay, so in our case, in the case of convolution operators, we ended up, what showed up for us, oh, I'm missing an absolute value there. It doesn't matter because they're supposed to be greater than 1. But we ended up, what showed up for us was logarithmic mean oscillation. Okay. So I was surprised about that, but then I did a little research and I noticed that other people have looked into logarithmic mean oscillation in harmonic analysis. So the first paper I found was in 1976, where Svante Jansson was trying to get bounds for multipliers in H1. And again, he failed to show BMO, but he was able to show logarithmic BMO. And Stegenga also had the same problem when looking at Topliss operators in H1. So for us, what we were able to show is that the generalized square function when we look in L infinity, again, if our parameters are strictly, so have a strict inequality, then we have a bounded mean oscillation. But when we have equality, and we have it for the square function and for the variationals, and when we have the quality, then you have to deal with logarithmic mean oscillation for both operators. So I was going to do the proof, but I'm already past my time. But so what do you think? Shall I go finish it?
You can carry on a little bit.
Okay, so what when you had to do the mean oscillation, what matters is what you get in this representation. So actually, so all what matters is to bound the difference of of the operator applied to 2 points which are close together. Okay, so and this difference is actually bounded by a square function on differences, on individual differences, I call it. So one can prove that if your operator is bounded in L2 and is dominated by the individual differences, like what I'm doing, what I just showed, and also and you have a handle on those individual differences. At least maybe you don't have it for everything, but you have it for functions. You're going to be handling points inside an interval, and the only restriction is that your function needs to be supported away from that interval, right? So the support of the function needs to be, so if I have my interval I, then I need to enlarge my I, and the support needs to be away. It could be there, and it could be there, right? So this is I tilde. So it's 3 times as large as the original one. So if the function is supported away from the interval and you're looking at points inside the interval and you have a handle on that, then you can prove a bounded oscillation result with this function as the rate function. So the kind of things for the convolutions, what it boils down to is to have a sequence of measures, right? And then one can prove that if actually you have control on the measures, on this infinite series of the measures, this one, because of technical reasons, just like I mentioned earlier, we had to take derivatives and second derivatives, but as long as you have a handle on the Fourier transform of these objects, um, then you're going to be able to control what you need. And what showed up for us is when we look at the second derivative term, this term shows up. And that's where the logarithm comes in. So sometimes we get logarithm, and sometimes we get something that doesn't depend on the L. So how do we prove it for the particular case that we're interested? Well, actually, this is a general proof. So I'm almost, I'm not going to show that, but what ends up happening is, again, we have to control the integral with the second derivatives. We have the infinite sum here of the littlest norms of the second derivatives multiplied by this factor. So the first thing is that what is this interval? What is this sum? And that one can argue that is of this form times this h prime. And when you multiply by this factor, you have two situations. So if you're near zero, what primes, you have this factor that helps you. And the near zero means when t is less than 1 over, I think it's L square. So if your t is less than this, you can do something. But when it is larger than 1 over L squared, this factor doesn't work, and the one that you have to use is this one, and then you're in trouble. So you're not in trouble if you have a strict inequality, but when you have equality, you have to integrate 1 over t, basically, essentially 1 over t, and that's where the logarithm comes from. So anyway, so that's why whenever you have equality, then the best you can do the best you can do is a logarithmic mean oscillation. And I only put the square function, but I have the same result for the variational norms. So the bounds are different, but I end up boiling down to the same thing. So again, So for the quality case, we have logarithmic mean bounded oscillation for S larger than 2. When S equals 2, we need to drop down to the oscillation norms. And I mentioned in the title jump inequalities. So the jump inequalities had to do with if you want to see the convergence of your operator, you want to see when your operator differs by a certain number, how many times your sequence of operators is larger than a particular number. But the good news is that when you try to control all the oscillations of your operator, then just by the definition of what this is and what the definition of the variation is the sum of the differences across any sequence that you can think of. So the number of jumps that you have is always dominated by the variational norm. So the estimates that we got for Wickel-1 and for logarithmic, and for the L infinity case also translates um, to the number of jumps. So I also ran out of time, I'm sorry. And this is
No.
it.
Thank you. Is there any? Okay, let me stop recording.